Hang on, let me start.
Shall we start?
Yeah, go ahead.
I'm very happy to welcome among us Professor Rajarama Bhat from the Indian Statistical Institute Bangalore Center. He is well known for his work on operator algebras, quantum probability, complete positivity, Hilbert modules, and things around those. I requested him to address a talk specifically to students at third year level maybe, but students nevertheless. So welcome, Raj.
Thank you. So I start.
Yeah.
So all of you can see the screen now, right?
Yes.
Okay. Okay. So I'm very happy to be here. So of course I would have been happier to be at Ashoka University, but let me start on. So as I said, this is meant for students, so it is at that level. So just a minute. It's stuck. Okay. So so in mathematics research, means there are two approaches we think about. One is the problem solving, so where you have sort of challenges, various problems to be solved, and some very hard nuts to crack sometimes. And you may also think about theory building, where you build the mathematical theories and it can be really big high rises. So, but things are not really disconnected. So when you want to solve some problems, you have to build the theory to solve those problems. And when you build theory, sometimes you come across hard problems and you have to solve them to go any further. Okay. And I used to teach sometimes some Math Olympiad students, and there the problem solving is the main goal. They don't care much about theory, but they need to solve various puzzles, problems. So there are various techniques as to how to solve problems, like this one, search for a pattern, draw a figure. All these things were listed in a book. So like formulate an equivalent problem, modify the problem, just various techniques. There are some 12 techniques listed in this book I saw. But unfortunately, when you solve a problem, you never go by one. Like you don't say that I'll first try the first method, then the second method. That doesn't work. You just think of some way of solving, some way or the other of solving the problems. And today I want to talk about one method. Is the method of invariance, which helps us to solve a variety of problems. And so I want to say what is this method, and just I'll begin with some examples. Okay, I will explain the whole scheme through examples. Okay, so the first example we call as the word problem. Maybe I can move this a bit. Okay. So this is taken from a book called Emperor's New Mind by Roger Penrose. He's a physicist, he got a Nobel Prize recently. So here is the given equations: eat equal to et, ate equal to a, later equal to lo, pan equal to pillow, carp equal to me, and you want prove lab equal to leaf. So this is in typical mathematics style. You have some axioms given, and from that you want to deduce the theorems, right? That is what happens in mathematics all the time. You have some things which you accept, take it for granted. Okay, this is obvious, we take this as granted. From that, we want to derive everything else. Okay, so this is a basic setup. And from that, you want to derive this. So this, let us see how to do that. So what exactly I mean by that. So this is what we want to prove, and what is given is this. Okay. So just to help you, I don't keep copying this every time. So this is given. We want to show lab equal to leap. So the proof goes like this, like you have lap. So then you have 8 equal to A. So A is same as 8. So I can replace this A. So whatever I'm replacing, I'm showing it in red color. So this A is replaced by 8. Okay, so ATE. So it becomes letter. So the words do not have any meaning, but we can make only these substitutions. In place of A, I can write 8 like that. Okay. So now I'm 8 equal to eat. So I can substitute this at by EAT. Then next I'm substituting this ATE with A again. So that becomes leap. So this way we have a theorem, lap equal to leap. Okay, very simple theorem, just 4 lines, and it uses only these 2 equations. Okay. Now, slightly more difficult theorem. So we want to show caterpillar equal to man. Okay. So we start with caterpillar and we substitute. So ATE has been substituted with A. So it becomes car. Next I substitute this A like that. Each time when I'm doing substitution, I'm showing it in red. So I'm substituting A here. So A equal to ATE. So that has been substituted. In the next step, I substitute this later. So later equal to rho. So it becomes rho, kilo. Next I substitute kilo like that. So each time you substitute. And so this way we prove theorems. Okay. So in fact, this is a general strategy in mathematics. So as I said, the axioms are given. From that we deduce all the theorems have to be deduced from the given set, right? Just like this. So this is several steps are needed. Okay. Now this kind of theorems, actually you can just give this to some computer to do these substitutions. And I'm sure once you give this data, the equations, the computers can do this kind of theorems much faster than us, right? They can try all these possibilities and substitute, and typically they would do it much faster than us. But here is the next theorem. We want to show that carpet is not equal to meat. Okay, so that means from carpet, whatever substitutions you do, like for A, I can put 8, then I do some other substitution. Whatever substitutions I do, I can never reach meat. Okay. Now this kind of theorem is difficult for the computer to prove, right? Because you don't know how to go. Means you can try 1,000 times or 1,000,000 times, you don't reach meat, but that still does not prove that you cannot go from here to here. Okay. So the question is how to prove this, that carpet is not equal to meat, because just the trial and error will not work. Okay. So how to prove this? So I want to show the method through some other examples where you can think of the solutions yourself. Okay. So here is a game. So there are 3 friends, A, B, C. So they are playing a game. So to begin with, A has 50 rupees, B has 100 rupees, and C has 200 rupees. Okay, 50, 100, and 200. And so they play some game. So whatever, say table tennis, badminton, whatever. But after each round, one of the player wins, and the winner gets 1 rupee each from others. For instance, if B wins, then A will give 1 rupee to B, so it becomes 49 here, and C also will give 1 rupee to B, so it becomes 102 here and 199 here, right? So we start with this, and after each round, the winner gets 1 rupee each from others. Okay, and the game continues like this. They play one more game, whoever wins gets 1 rupee each from others. Okay, the question is it possible that A, B, C have 100 rupees each after some rounds? Okay, so we started with this 50, 100, and 200. So each time the winner gets 1 rupee each from others. Okay, so normally I would get response from audience, but now this is difficult. So we say it is impossible, right? So why do you say it is impossible? So we see that the friends together have a total of 350 rupees in the beginning, and this sum remains same throughout, right? So totally they started with 350 rupees. So the winner gets 1 rupee each from others, but that doesn't change the sum. So there is no way, so it can change. The sum would remain invariant. So the total is an invariant here. It is not changing through the steps of the game. Okay, so we can't reach 100 each starting from this, because here the total sum was 350, and there is no way to end up with this because the sum cannot change. It is an invariant. Okay, so here is a different game. So that is the fun of this. That is in this previous thing, I should say, because nobody asked you to look at the sum, but one would just instinctively think of, okay, sum is not changing. Okay, it is not given in the problem that you should look at the sum. So the computers won't be able to do that, but you can see that it works. So here is another game of similar kind. So there are 2 bags with balls in them. So the bag 1 has 25 balls. The bag 2 has 30 balls. Okay, so you toss a coin, and if it heads, you add 1 ball each to the bags. Okay, so if you get head, so then you have a large supply of bags. Okay, large supply of balls. So if it is heads, you put 1 ball each. So this would become 26 and 31. If it is tails, you remove 1 ball each from the bags. Okay, so it will become 24 and 29. And you continue like this. So we ask, is it possible to reach 20 and 30 after some tosses? Okay, so see the game. So started with 25 and 30. Okay, so either you add 1 ball each or you remove 1 ball each. And can we reach 20 and 30? So again we say no, because the difference is an invariant. The difference from, say, the number of balls in bag 2 minus the number of balls in bag 1, it would stay as 5 all the time, right? The sum is no longer an invariant. Okay, the sum is changing because either you're adding balls or removing them. The sum is changing, but the difference is an invariant now. Okay, so that is the idea. So what is this concept of invariant? Okay, what is an invariant? So I give the mathematical setup for that. So consider a set S. So I'm saying S is where the action is taking place. Like in the first game, the game where 3 friends A, B, C, the money each they had. So the triple, the money they had, that is the set S. Okay, like they had some 50, 100, and 200. So that triple. Okay, so that is the set S. Okay, so for X, Y in S, we write X is equivalent to Y if we can go to Y from X after some steps, right? So from whatever triple you had, where all you can go after some steps. So that is, you say X and Y are equivalent. If you can go to Y from X, then we say that X and Y are equivalent. It means that in the game, in your game, it is possible to go from X to Y. So we assume the following things. Namely, first of all, X is equivalent to X. So like you can stay at X if you wish to. Okay. And if you can go from X to Y, then it's also possible to go from Y to X. Okay. So we assume that. And then if it is possible to go from X to Y and Y to Z, then it's possible to go from X to Z. Okay. So this is called transitivity. We assume this. So if you have done a little bit of mathematics, you would have seen this kind of thing. This is called an equivalence relation, right? So on a set S, we have an equivalence relation, right? So X is equivalent to X, X is equivalent to Y, implies Y is equivalent to X. So you have to adapt it to your game, and the possibility is there. So this is the meaning. Okay, so we call this as an equivalence relation if these three properties are satisfied. Okay, so now I can define invariant. So consider a set S with an equivalence relation. So then S partitions into equivalence, S partitions into equivalence classes, right? So X and Y are in the same class if and only if X is equivalent to Y. So that is our definition. So we say that X and Y are in the same class if X is equivalent to Y. So that way whole set S partitions into various classes, right? You can see it for yourself that with any equivalence relations gives you a partition of the set. Okay, in this way, this is a definition. X and Y are in the same class if X is equivalent to Y. Now we choose another set T. It is your choice which set you want to choose. A set T where our invariant would take value. So a function f from S to T is said to be an invariant if X is equivalent to Y implies f of X equal to f of Y. In other words, if X and Y are in the same class, f should take the same value. Okay, so X and Y in the same class, f should take same value. We call it a complete invariant if you can go backwards also. F of X equal to Fy implies X is equivalent to Y and vice versa. Okay, X is equivalent to Y if and only if f of X equal to f of Y. Then you call it a complete invariant. But typically we just have an invariant to start with, namely X equivalent to Y implies f of X equal to f of Y. So if f is an invariant and f of X is, this is the main thing to note, namely if f is an invariant and f of X is not equal to f of Y, that means X and Y are in different class, because our definition of invariant says if X and Y are in the same class, f should take same value. So as soon as you know that f takes different values at X and Y, you know that X and Y are in different classes. So f gives you a mechanism, a testing mechanism to see whether X and Y are in the same class or not, right? So as soon as you know that f is taking different values, you know that X and Y are in different class. Okay. With general invariant, you cannot say f of X may be equal to f of Y, but X and Y may still be in different classes. Only in complete invariant you can go other way, but most of the time you apply the result in this way, namely f of X not equal to f of Y implies X and Y are in different classes. Okay, so if you see our examples, solutions to examples, like the sum game, we had three friends playing a game. So the money they had, each one, the three friends had, that is the set S, A, B, C. So where all it can move. So the set S I take as triples of natural numbers. The T I am taking as the sum, the set of natural numbers, and the invariant was just the sum, f of A, B, C equal to A plus B plus C. And you see that in each step of the game, this sum remains invariant. It doesn't change. So two triples, A, B, C and another D, E, F are in the same class if it is possible to go from A, B, C to D, E, F. So we see that if it is possible, then the sum should be equal. So this F is an invariant there. In the different game, the S is a pair of natural numbers. We had two bags with balls. Okay, the balls in first bag and the second bag, that is the set. Okay, and we say call S as the system, the states of the system. Okay, so then f of AB is B minus A, the difference. Okay, so and we saw that for this game, the difference is an invariant, it's not changing. So now we can give the solution to the world problem. Okay, so what was given was this: it equal to at, equal to A, letter equal to low, pan equal to kilo, carp equal to me. So SS, take SS all possible words with this kind of alphabet. Okay, A, B, C, W, all words you take. So define F on S by this. For any word X, you define F by number of A's plus number of W's plus number of M's. in the word X. Okay. So like f of eat, you just count the number of A's, add it with number of W's plus number of M's. So this has just one A, no W or M. So f of eat equal to 1. Same with f of et. In fact, all these words are giving you the value of f as 1. Okay. All the things here. Okay. So now, whenever in a word, when you make a substitution, so you will be replacing one of these words with another word. So the value of f will not change. So any substitution, whichever substitution out of this you make, the value of f just won't change. Okay. So it is an invariant. And we wanted to show carpet is not equal to meat. And you see that f of carpet is 1 and f of meat, because number of A's plus number of M plus number of W. So f of meat is 2. So there is no way of going from carpet to meat, because anytime you are doing the substitution, the value of f, okay, it would always remain 1. It cannot jump to 2, right? No substitution changes the value of f. So it is an invariant. So because of that, it's not possible to go from carpet to meat by any number of substitutions. So we have a proof of this theorem, carpet not equal to meat, just using this concept of invariance. Okay. So there are any questions at this point? So now I move over to more mathematical problems. So a few programs I will talk which uses this kind of invariance. So one is this ISBN numbers. Like most published books, if you see, the number, code number called ISBN number, like this book of Penrose I spoke about, has this number. Okay, a 10-digit number. Okay. So given any such ISBN number, say the digits as D1, D2, etc., D10, you look at D1 plus 2 times D2 plus 3 times D3, etc., 9 times D9, and you divide it by 11, the remainder would be the last digit, the D10. Okay. So given this, so you take the first one, then 2 times second one, like that, you add this up, divide by 11, you look at the remainder. The last digit would be the remainder. So why this was done this way? The idea is that when you communicate this ISBN number through email or somewhere else or by phone, then if there is some small error, it should be possible to detect it. Okay. So like if you change one of the digits here or interchange 2 digits, you will be able to detect. Okay. So that is the idea. So it's the error correction, just for correcting, just to error detection. Okay. So what is the invariant here? Is the remainder. When you divide this minus D10, when you divide by 11, it's always 0. Okay. So that for valid ISBN numbers. Okay. So it's really a practical application of this concept of invariance. So only those numbers which give you this value as 0, okay, this computation D1 plus 2 times D2, etc., this divided by 11, the remainder. So only those numbers where the remainder is 0, they are valid ISBN numbers. Well, in recent years, the ISBN numbers have more digits because this was not enough, and there are more complicated invariants. Okay, so I don't know precisely what there are, but I know there are more complicated invariants used there. Okay, so this is a genuine application of the concept of invariant. So I told that the students have done some matrix theory. So here is one question from matrix theory. So I have 2 matrices A and B, 2 by 2 matrices. So the question is there a unitary matrix U? So unitary means U times U star being the conjugate transpose. You take the transpose and then take complex conjugate of each of the entries. So UU star equal to U star U equal to identity, then you call it a unitary matrix. These matrices come when you change the basis from one orthonormal basis to another orthonormal basis. That is when you get these unitaries. So the question is there a unitary such that you can go to B from A, B equal to UA U star. So from a change of basis from A, can we reach B? Okay, so that's the question. What you see is that if X is normal, normal means XX star equal to X star X, X commutes with its adjoint. Then UX U star has to be normal. Just multiply this and see check the normality for UX U star using these properties, and you see that if X is normal, then UX U star is also normal. So the property of being normal, that is an invariance. Okay, if you start with a normal matrix, you do this transformation, conjugation by unitary, then it would remain normal. Okay, so that is an invariant. And moreover, the eigenvalues of X and that of UX U star have to be same. So here eigenvalues, all the n eigenvalues, the counting multiplicity, the roots of the characteristic polynomial. Okay, so like if an eigenvalue comes twice in the characteristic polynomial, you have to count it twice. Okay, so counting multiplicity, the eigenvalues are of X and UX star U star are same. So that actually tells you that this A and B are not conjugate. You cannot go to this B from A because this matrix is normal, whereas B is not normal. Also, if you look at the eigenvalues of A would be 2 and 1, the diagonal entries. The same with B, eigenvalues of B are 1 and 1. Okay, so it is not possible to go from A to B. Okay. In fact, the collection of eigenvalues, including multiplicity, is an invariant. It is actually a complete invariant within the class of normal matrices. Okay, so if two matrices are normal and have same set of eigenvalues, it is possible to go from one to another through a unitary. Okay, like this kind of conjugation. Whereas if there is a closely connected concept called similarity. If A and B are similar, so that means there is some invertible matrix S, not necessarily unitary. Right here, U is unitary means the inverse is U star, but here it can be any invertible matrix S. Then also A and B would have the same collection of eigenvalues. However, it's not a complete invariant anymore. Okay, whereas in this case, it is a complete invariant within the class of normal matrices. Okay, so here is another famous invariant called Euler characteristic. So you consider a simple connected planar graph. Simple, I don't mean, means we don't want directed graphs and things like that. So just think of some cities connected by roads, but no flyovers, underpasses, etc. It's a planar graph. Drawn on a plane. Okay, you can draw it on a piece of paper like that. Okay, so I don't want edges crossing each other. Okay, so take V as the number of vertices, E as the number of edges, F as the number of faces or regions, including the exterior, and then V minus E plus F equal to 2. So this is a theorem of Euler. So let me give an example. Okay. So here is an example. So in this graph, I have numbered only the regions. Okay. The vertices, there are 7 of them. 1, 2, 3, 4, 5, 6, 7. So 7 vertices. Edges, 13 of them, like all these red edges. Okay. And you see here, I need to have a vertex. Okay. I cannot have just edges like this, then it won't be planar. You should be able to draw it on the plane. Okay. So it cannot cross like this without a vertex there. And F is the regions or the number of faces, like this region, 1, 2, 3, like that. And this 8 is the outside or the exterior. That is also counted. Okay. And you can see that V minus E plus F. So 7 minus 13 plus 8 is equal to 2. And each time, so you add, say, you want to add one more vertex and some edges like that. If you add, you can see that this relationship is always remains. You cannot change it. It is always V minus E plus F equal to 2. Okay. So, right. So for instance, it is impossible to have a simple planar graph like this with V, E, F all equal to 100. Okay. So now it's if you give this problem to a kid, it's find it very difficult, to check whether it's possible with this to have this or not, right? Means you cannot directly check. But with this formula, it's very easy to see that it is impossible to have a graph where you have these properties, right? V, E all equal to 100 because it won't satisfy this. So here the invariant number is 2. It's an invariant of the plane. So we are saying we are talking about only the graphs on the plane. So if you take torus or more complicated surface, the invariant would change. Okay, and there is a lot of deep mathematics generalizing this and extending this concept. So IR characteristic is the sort of starting point there. Okay. So generally in mathematics, means invariants are very extensively used to classify mathematical objects. They need not be just numbers. So one famous invariant is this thing called Jones polynomial for knots. Okay, which tries to classify the knots, different knots, the three-dimensional things, the usual knots, how to classify them. The invariant is a polynomial. So, well, a polynomial is just a tuple of numbers. So you may think of it as a tuple of numbers. It was discovered by Van Jones, who died just recently, just I think 2 months back. And actually, instead of just being numbers or tuples of numbers, the invariant can be a group or a ring or some other algebraic structure, right? It need not be a number. It need not be a polynomial. It need not be one object like that. It can be the whole structure itself. In fact, Galois groups were used by Galois to show that it's not possible to write down the roots of some high degree polynomials, right? Polynomials with degree greater than or equal to 5, it is not possible to, at least some of the polynomials, it's not possible to write down the roots the way you do it for quadratic polynomials, where you can write down all the roots. Okay, you have a formula. You don't have similar formula for higher degree polynomials. So see the problem there. See, when you want a formula, you exhibit a formula and say this works. But you have to show that there is no formula. How do you do it? Okay, that is the hard problem. Okay, it is similar to the first problem, the word problem we said. You cannot go from carpet to meat. How do you show that it's impossible? Okay, so the same thing kind of problem here. You have polynomials and you want to show that it is not possible to write down the solution. And how do you show? Okay, so that was a real hard problem, and the Galois groups allows you to show it precisely as to when it is possible and when it is not possible. So the group itself is an invariant. So actually groups appear as invariants in many fields of mathematics. So some of you may have seen this concept called fundamental group as an invariant in topology. But again, it need not be groups. Invariants can be sort of any sort of object. Just only our imagination is the limit. The point is that for the given problem, you define the invariant, but it's not good enough to define the invariant. You should be able to compute it and compare them and see that things are different or same. Okay, so they are the problems. One has to come up with a good idea of an invariant, and then one should be able to work with it. One should be able to compute it and compare them. Okay, and sometimes it's really hard. Okay, and now I move to a problem where there is no good invariant, and that creates some problems. Okay, so here is something called Banach-Tarski paradox. Just look at the claim. So we are saying start with a solid golden ball of certain radius r. So the claim is that we can break the ball into few pieces. In fact, 5 pieces would be enough, but a finite number of pieces is the important thing. A few pieces, and rearrange the pieces so that you have 2 solid balls. That itself may not be that surprising, but each of radius r and identical to the ball you started with. Okay, so these are not of smaller radius, but the same radius. Okay, so that sounds impossible. So, well, again, when it sounds impossible, how do you try to prove that it is impossible? Well, you would think of here, would think of the volume, right? That you would say that maybe the volumes of the pieces which you add up should be the volume of the original ball. Okay, so here it has certain volume. Here, when you have 2 solid balls, the volume would double up. So that is an invariant, right? It is true, it is an invariant, it works fine, provided these pieces are good which have volumes. See, what is volume of a piece? It's like the area of a region you define. So like if you want area of certain region drawn on plane or drawn on paper, you sort of approximate it using squares or rectangles and define the area. Same way the volume, you can try to approximate using cubes, you make small cubes and try to approximate the volume. But it is possible that the pieces can be so strange, so peculiar that they have no volume. Same way there are regions so bad that it has no area. Okay. There is a distinction, like if you take a small line, the volume, I don't say that it has no volume, it has the volume 0, but the no volume means there is no way of approximating things the way it works. Okay, so such things are there, and there are also regions with no possible area. Okay, so it's actually a theorem of, so I called it paradox because it looks strange, but it's actually a theorem of Banach and Tarski that what has been claimed here is actually possible. Okay, it's not a conjecture or anything, it's actually a theorem that it is possible to double the balls like this. Okay, so my goal in next 20 minutes is to give you some idea of this proof of this. So just the idea, I cannot give a full proof. In fact, I don't know the full proof actually. So, but I know roughly how it goes. So here is something which some of you at least familiar. Look at the set of natural numbers. Look at even numbers. Okay. So how many even numbers are there? You might say half the number, but that is not true, right? So like this is the first even number, 2, second, third, fourth. Like if you count, you would see that there are as many even numbers as there are natural numbers, not small. Okay, the total number of even numbers is just same as the natural numbers. You just count it, the first one, second one, third one, fourth one. So that way, when you want to count, you just did just this many numbers, right? So if you look at odd numbers, the same thing. There are as many odd numbers as there are even numbers, and there are as many odd numbers as there is the set of natural numbers. Okay, so it is not smaller. Okay, so that is what happens, can happen very easily for infinite sets. So here the natural numbers is the union of these two, even and odd. They are disjoint, and the even numbers, there are as many even numbers as there are natural numbers. There are as many odd numbers as there are natural numbers. So all these sets have same cardinality or same number of elements. Okay, N, E, and O. Okay, so it is possible. So from N, I have broken up into 2 pieces, E and O. disjoint pieces, both of them are as big as n. Okay, so such things can happen set theoretically. Right? So it says such things are possible with infinite sets, right? The set of natural numbers you break up, and both these sets have just the same number of elements. So similar thing happens in intervals. See, the closed interval 0, 1 and 0, 2 have same number of elements, because you just look at this function from 0, 1 to 0 to 2, f of x equal to 2 times x. Then you just have a mapping. So from here to here, which is bijection, 1 to 1 and on 2. And if two sets have a bijection, that means they have same number of elements, right? You can just renumber the elements here by this, or you can renumber the elements here. Each x, you may call it 2 times x, and you will have same number of elements. So again, 0 to 2, you can break it up like this. 0 to 1, I have put 1 open, excluding 1, just to make this disjoint. And you see that all these have same number of elements, all these sets. Okay, 0 to 2, 0 to 1, 1 to 2. So set theoretically, such decompositions are actually very easy to combine. Okay, it might be surprising in the beginning when you just learn set theory, but very quickly you will see, okay, this is quite feasible for infinite sets and very common. However, what is claimed by Banach and Tarski is much more intricate. Okay, it is not some set theory like this, because the point is that we are allowed to divide the ball only to finite number of pieces. So if you just count the number of points in the ball, like a ball of radius r and 2r, all of them will have the same number of points. Okay, just as many points as there in the interval 0 to 1. Okay, the balls also would have just same number of points, but that is, they are all infinite points, but it's the same number. Okay, it's a, but here you are allowed to divide the ball only into finitely many pieces. You cannot break it up into each all the points. And moreover, when you rearrange, you are moving around the pieces in the space without disfiguring them. Like this kind of stretching the interval, such things are not allowed. Obviously, if you can stretch, you can make it bigger. Okay, but that is not allowed. Okay, only rotations and translations are what is allowed. Okay, the similar thing we can do with paper cutting. Okay, so start with a piece of paper with a polygon. I had given one such puzzle in the abstract. Okay, so with some polygonal shape, cut it into smaller pieces. Okay, but I want to have each piece to have some kind of polygonal shape. So rearrange to a new shape. So see, when you have polygonal shape, then you can just break it up into small triangles and you can compute the area. So it's clear that any such rearrangement, area is an invariant. Area will not change, because if you cut into pieces with polygonal shape, each one of them will have an area. So it is easy to see that the area will not change. So question is, can we have from a shape, say, of area, say 15 square centimeter, can you move to another one, some other shape, polygonal shape with area 15? Okay, is that all? Is it a complete invariant? Is area a complete invariant? Answer is yes. And this is a theorem called Vegas, Bogai, and Galvin theorem, that here area is a complete invariant. So what it means is that, just I said, Banach and Tarski can double the walls, but you cannot double the currency notes by cutting them into few pieces and rearranging them. Okay. But here is something you can do if you don't restrict to polygonal shapes. Okay. So then some things possible. So here I just want to illustrate a procedure in 2 dimensions, which does a small miracle, I can say. So we will cut a disk into 3 pieces, okay, in such a way that when we rotate and rearrange second and third pieces suitably, we have the full disk back. So I have cut the disk into 3 parts. The first part you leave it aside. Only the second and third you rearrange, just rotate and rearrange, and you get the full disk back. So the first piece becomes an extra piece. Okay. So we are not able to have two disks, but at least we get a small piece extra. Okay, so the disk, you put it in the complex plane. So the set of all complex numbers of modulus less than or equal to 1. So we want to write into 3 pieces. This notation here, the union with the plus just means that it's a union of disjoint sets. Okay, so we want to write D as union of 3 disjoint sets, A1, A2, A3. So A1 is the small piece which I want to remove. So this is just the unit interval. Okay, in the disk, the real line, the real numbers between 0 and 1. Okay, so that is A1. And I will write D also as B2 union A3, disjoint union. So I will not rotate A3, I will rotate only A2. Okay, so B2 will be a rotation of A2 and you get the full disk back. Okay, so the method is you choose an irrational theta between 0 and 1. And the observation you have to make is that if you take e to the power 2 pi I theta n, for different natural numbers, these values are different. Okay, so that is just follows from the irrationality of this theta. Just work it out. And so here is some formula I have given, but I can explain it much better using a picture. So here is a picture. Okay, so what we do, so from the full disk, I will be removing this line, the real line, the blue line. So that is to be removed. Okay, so what is the second piece? The second piece is to take this angle theta, which is an irrational angle. So this line is part of the second piece. The whole is the circle, the outside thing. And then this line, this angle theta, then 2 theta, then 3 theta. So you get this line first. So these are like spokes of a cycle. Okay, so you take this spoke, then this one, then this one, like that. Angles are theta, 2 times theta, 3 times theta, like that you go. When you choose irrational theta, you don't match with the previous one anytime. Like I go to 5, then the 6th one will not come to this x-axis. It will go somewhere here. It will not match with this. It will go somewhere here. All of them would be distinct. So that means I would get infinitely many spokes. Okay. So the second piece consists of this rim, the outside circle, as well as this infinitely many spokes. Okay. The first piece is this, just the x-axis, this part. And the third piece is the rest of whatever is there in the disk, which we leave untouched. We just leave it as it is. What we do, you remove this blue line, remove it, and this, the cycle wheel, you just rotate it by minus theta. So you bring this one to here. So this line, this will come here. The line 2 will come to 1, 3 will go to 2, 4 will go to 3. Like that, you just rotate it backwards, okay, clockwise. Just rotate it by an angle theta. So then you have covered everything. Nothing is missing because this part which has been removed gets covered by 1. The 1 gets covered by 2, 2 gets covered by 3. Like that, whole disk gets covered. Okay, and you have one small piece extra. Okay, so that is the procedure, and that has been written down mathematically here. So the A2 consists of the circle, the rim, and these spokes. Okay, and A3 is the rest. Okay, and you can check that it works. Just you have to rotate the second piece by an angle minus theta. Okay, and then you are done. Okay. So we could extract a line out of the disk in 1 or 2 dimensions. It's difficult to do more, but in larger dimensions, we have more freedom. There are group theoretic reasons for that. So generally, when we are rearranging pieces, we are considering translations and rotations. Okay. So these are what we call group actions. So if you have a space, topological space, say, like Rn or anything, or the ball. So by an action of a group, we mean rotations or translations, right? And so for every element G, you have like X goes to X rotated by G or X translated by G, like that. And it should be that you rotate by H and then rotate by G, it will be rotation by G times H, like that. Okay. So, and E is the identity. So then you don't make any change. Okay. So to handle these rotations efficiently, we need to look at group actions on the unit ball, and to get the kind of results we want to get, this group should be rich enough, big enough, and that is not possible in the plane, but in the sphere case it is possible. And the group you need are what are called free groups. So here we are considering the free group with two generators called F2. So what is it? So you have two generators of two abstract elements A and B, and E is the identity, and the F2 consists of all products of A and A inverse. So these are just abstract symbols. Okay. Only relations you assume is that A times A inverse should be the identity, A inverse A should be identity, A times B would stay as AB. Okay, like that. So if you multiply tuples like this, you would get AA, then B 4 times, because A and A inverse would give you identity. So that would go away. But unless you get the identity somehow like that, there are no other cancellations. Okay. So if you think of this, the F2 will consist of all sorts of elements like this. It will start with the identity, then some powers of A, okay, including negative powers. Okay. But I am excluding the 0th power because E is already counted there. So I'm just taking non-zero powers. So you may start with A and end up with A, or you may start with A and end up with B, or start with B and B, or start with B and end up A. Okay, so these are all the elements of F2. So you may think that it's too abstract. So I'll give you a concrete representation. Okay, maybe I can make it bigger. Okay. So we can get using matrices. So take A as this matrix, 1 to 1, B is another one. So you can see that A and B are invertible. In fact, for every integer n, A to the power n, you multiply and compute, and you see that it is the matrix 1, 2n, 0, 1. So you are taking product here, but it gets added up here. Okay, this is true including for n negative, right? N equal to 0 gives you the identity. So A to the power minus 1, that is the inverse of A is 1 minus 2, 0, 1. Same thing with B, I think here. So the group generated by A and B by taking all possible products and inverses, so that is group F2. Okay, so the proof is not easy. You have to show that all sorts of products which you get here, they're all distinct. Okay, so that can be an interesting exercise. Just involves just matrix products. Okay, and it's often proved by using a result called ping pong lemma, but I will not go into the proof. But it's an interesting thing to see that this actually gives you the F2, the free group with two generators. So it is, though our definition was abstract, it is really not all that abstract. You can see them even with 2 by 2 matrices. Okay. So let G be a group, then we say that it has paradoxical decomposition if there are subsets A1, A2, B1, B2, all disjoint 4 subsets. Okay. So the G may not be the union of all these 4 disjoint pieces. It might have something extra. We don't care about that. Okay. So if you rotate this A1 and A2 suitably, you should get back G. Okay. So G1 A1 is A1 rotated by G1. G2 A2 is A2 rotated by G2. So there should be some group elements so that if you rotate them, you get back G. Same way with B1 and B2, you get back G. So you see, A1 and A2 are so big that after certain rotations, their union gives you whole of G. Same with B1 and B2. So A1 and A2 are together as big as G, B1 and B2 also together as big as G. So that's why it's paradoxical. Inside G itself, you have got 2 parts which are almost as big as G. Okay. So this can be done in F2. F2 has this kind of decomposition. by SA, I denote the elements of F2 which begin with A. Okay. Similarly, I can define as A inverse, SB, SB inverse. The group elements starting with A, starting with A inverse, starting with B inverse, like that. Okay. So then you can see any element of the group, this F2, okay, G is F2 here, is either identity or starts with A or starts with A inverse or starts with B or starts with B inverse. So it has to be one of these. Okay. So you now suppose it starts with A and you start with that, you add this thing starting with A inverse multiplied by A from the left. Okay. So that can includes, for instance, the identity, because just A inverse is here. Okay. So think about it. When you multiply as A inverse by in the front from A, I will generate E. I will generate S of A inverse. Anything starting with A inverse also can be got by putting some extra inverse here. So everything of this kind can be generated. In other words, G is the union of this disjoint union. Same way with this, the disjoint union. So in other words, F2 has a paradoxical decomposition like this. Okay. So this is A1, this is A2, B1, B2, like that. Okay. So it has a decomposition like this. So Banach-Tarski theorem uses this paradoxical decomposition F2 and could double the unit ball. The conclusion, my time is up more or less. The conclusion is that to double your goal, you should learn some mathematics. And also you should have some really fine tools to break it up into that very fine pieces, okay, which have no volume. Okay, so here are some references. Thank you.
Excellent, very nice talk.
Yes.
Yeah, thank you, sir. Very, very good. I wish there were more students, but there were, I think, at least a few. Yeah. Any questions?
Yeah, I think you can.
One.
Engage as a question.
Yeah.
So I'll stop share.
Hang on. I think Gurgesh has a question.
Yeah.
Yeah, I have a question. So
Yeah.
define invariant. Why we needed to define the equivalence relation first, so that to capture the notion of complete invariance, because we could have directly said that like in the sum game, the sum of the three things will be invariant. Even if like.
No, so you suddenly thought of the sum. So you need a mathematical framework how to do this kind of things, right? So in general, so the idea is that if it is the value of f are different, then you cannot go from one to another.
Okay, so the complete invariant means that if the f takes the same values, then it is
f takes the same values, then it is possible to go from one to another.
Okay.
Like in the word game, two values of f is same equal to 1 does not mean that you can go from one to another.
Yeah,
right.
But in the case of matrices, we can unitary transformations.
Yes. Yeah. So complete invariant is definitely more useful, but usually hard to come by. And so there is this famous problem about these free groups. He started with F2. Similar thing one can do with the 3 elements, 4 elements like that. So with Fn, okay, there is also an F infinity with infinite number of generators. So starting with free groups, one can generate what is called the algebra of that, something like with the matrices. You do it, generate the, you take their linear combinations and that kind of thing. So then the group algebras generated by this for different n and m, is it possible that they are isomorphic or not, whether they are distinct or not for n not equal to m. No? That is called the free group isomorphism problem. So n not equal to m, then we know that Fn is not equal to Fm. But is it that when you generate the things, the algebras, whether they are same or distinct? So that problem is still open. Nobody knows. But the many invariants have been constructed. What comes out of one invariant is that either all of them are same or all of them are distinct. So we know that either all these Fn's, including the Fm, if you generate the algebras, either all of them are same or all of them are different. But we still don't know whether they are distinct or not. I'm not talking about the groups themselves, but the algebras generated by them.
Any other comments? I think Ajit Iqbal Singh has some.
The algebras with what coefficients?
Yes.
Okay.
The result that you mentioned is the group algebras with what coefficients?
With
With
no,
which
with
coefficients?
Yeah, with coefficients. We generate what we call von Neumann algebras from these free groups.
Yeah.
So you have to take closures, not just a group algebra and
So not just the group algebra, but the von Neumann algebra, you mean?
von Neumann algebras, yes.
Okay. Because for group algebras, it would be true.
Yeah. You have to completion. After completion, we don't know whether they are distinct or same.
That's right. You go as far as the von Neumann algebras.
Yes.
Okay. Thank you.
So any other questions and comments?